Hi everyone. This video is just a very brief introduction to gas chromatography, mass spectrometry, and I really just want to illustrate the power of GCMS in this video. So here is the GC portion, and here is the mass spec portion of the instrument. And we'll talk in great detail about each component of a mass spec, the ion source, the mass analyzer, and the transducer a little bit later, but I just wanted to give you an overview again of the power of GCMS. So let's imagine that we injected a standard that contained some known concentration of bisphenol A, that's what BPA is, along with an internal standard. Here is the injection port in our GC, and our solutes flowed through the column and got separated. And let's imagine that the bisphenol A eluted first. It now enters the mass spec where it gets ionized. And what I've crudely tried to show you here is that sometimes that ionization process is so energetic that the analyte gets fragmented. So again, I'm just doing this kind of crudely. B plus and PA plus are just fragments of BPA. And notice that I did leave one intact BPA ion. So after our solute gets ionized, it passes through the mass analyzer, and those masses get sorted, and then those ions reach a transducer where ions get converted into an electrical signal. So in order to create a chromatogram, we're monitoring the detector the entire time. So the response then is going to be ion intensity or abundance as a function of time. And let's imagine that this signal represents all of the ions associated with BPA. There they are again. The power of mass spec is that you get additional information. Not only do you have ion intensity over time, but you can look closely at this peak and look at ion intensity versus mass to charge ratio. So you can see that I've indicated that B plus is the smallest ion, followed by PA plus, and then the intact BPA ion. Now, why is this so powerful? The fragmentation patterns that you see in your mass spectrum can help to qualitatively identify a solute if needed. So we get a lot more information from mass spectrometry when it's connected to a GC. And again, we'll talk about each of these components in a mass spec in great detail later. I think you've seen this figure before where this rising baseline is column bleed. And if you were to take maybe a mass spec of one of these peaks, you may see some evidence of column bleed. What I'm seeing right here at a mass to charge ratio of 207.1 probably corresponds to this trimer of stationary phase that eluted off the column and now appears in our mass spectrum. Again, this wouldn't be possible with any of the other detectors that we talked about, only with mass spec. So one final slide to kind of tie things together. We're looking at a figure where we have different types of columns with different types of stationary phase thicknesses, which again is related to that sample capacity. And we've also got various detectors down here. Now, the typical mass that gets injected into a GC is about a nanogram. And what is this figure showing? you can use stationary phases as thin as zero point 0.1 micrometers, but the TCD detector isn't sensitive enough. The FID will work. The ECD detector will not respond to something as big as a nanogram, but the mass spec will. Now, if we were to dilute our mass injected maybe by a factor of 100, that would in fact move us into the range where the electron capture detector worked. So again, I really like how this figure summarizes some of the things that we talked about related to columns and detectors. That's it for this video. Thanks for listening.